All right, let's get right into it. Today, we're going to crack the code on something you see literally every single day: digital images. We are pulling back the curtain on how everything, from the photos on your phone to the videos you stream, is actually built. So let's dive in.
I mean, really, stop and think about that for a second. You tap a button, right? And the real world in front of you becomes this flat digital file you can send anywhere on the planet. How does that even work? It feels like it should be magic, but it's actually something way more clever.
Because here's the thing, once you get the one fundamental secret behind every single digital image, you unlock the power to change it, to analyze it, and even to teach a computer how to see it.
And there it is. That's the big secret. Every single picture you've ever seen on a screen is, at its core, just a massive grid of numbers. Yep, a giant spreadsheet. Each number tells the computer the brightness of one tiny dot, 1 pixel. 0 is pure black, 255 is pure white, and all the numbers in between are just different shades of gray. This one idea is the key to everything we're about to do.
Okay, so if an image is just a bunch of numbers, you know what that means, right? We can do math on it. So let's start with something we've all wanted to do. Take a photo that's just kinda meh and make it really pop.
So take a look at this photo. It's dark, it's muddy, you can't really see the details in the shadows. Now, what that actually means, in the language of the computer, is that all its pixel values, all those numbers, are crammed together in a really narrow, dark range. We're not using the full palette of light that's available to us.
To fix this, we can use a really simple but incredibly powerful trick called point processing. It's basically a one-to-one deal. We look at a single pixel, check its original number, and run it through a formula to give it a brand new one. It's a solo mission for each pixel. We don't care at all what its neighbors are doing.
Now, this graph here is called a histogram. The easiest way to think about it is as a census for all the pixels in our image. The horizontal line at the bottom goes from total black to pure white. The height of the bars tells us how many pixels live at each brightness level. And right now, as you can see, our pixel population is all crowded into one neighborhood, the dark one.
So, how do we fix this? With a super elegant solution called histogram stretching. It's a 3-step process. First, the computer finds the absolute darkest and brightest pixels that currently exist in the picture. Then, it creates a new map to stretch that small, cramped range all the way out to the full spectrum, from 0 to 255. And finally, it applies that new map to every single pixel in the image.
And boom, look at that. The image is bright, it's clear, it has contrast, and now look at the new histogram. Our pixel census is beautifully balanced. The population is spread out across the entire range of brightness. We didn't invent any new information. We just redistributed the data we already had to make it look way better to our eyes.
Okay, making a picture brighter is cool, but what about teaching a computer to actually find things in the picture? Well, for that, a pixel can't just think about itself anymore. It has to start paying attention to its neighbors. And that brings us to the next big idea.
And this right here is the critical difference. Point processing, what we just did, was a solo act. Neighborhood processing is a team sport. A pixel's new value isn't just based on its old one, it's based on its old one plus the values of all the pixels right around it. This is how we go from just tweaking an image to actually understanding what's inside it.
This is the absolute foundation of computer vision. You know when you take a picture and your phone instantly draws a little yellow box around someone's face? That's not magic. It's an algorithm that's looking for patterns, like the sudden change from light to dark that makes up the edge of a nose or a jawline. So, how does it actually do that?
It uses a tool called a kernel. And a kernel is really just a tiny grid of numbers, maybe 3 by 3. Think of it like a special magnifying glass or a recipe that's designed to find just one specific thing. You slide this little kernel over the entire image, pixel by pixel, and at each stop you do some simple math. The result tells you if the pattern you're looking for, like a sharp vertical line, is there.
So, let's take this photo here. To us, it's obviously a person. We see a face, hair, shoulders, easy. But to a computer, it's just that giant grid of numbers we started with. It has zero concept of person. But now, watch what happens when we slide an edge-finding kernel across the whole thing. The image you see now is what the computer produces. It has highlighted every single spot where there was a dramatic change in brightness. Now, it hasn't found a person, not yet, but it has found the fundamental boundaries that make up the person. This is the very first step toward a computer actually being able to see.
Now we can take this exact same logic of finding differences and apply it to video.
The only real change is that with video, we're usually looking for the difference between one moment in time and the next.
I mean, that's all a video really is, right? It's just a slideshow of still images. We call them frames, flickering by really fast. For a computer, this is awesome. It's just a long sequence of those number grids it already knows how to handle. So the most basic thing we might want to do is tell it to ignore everything that's standing still and only pay attention to what's moving.
And a really classic way to do this is with a technique called background subtraction. It's so clever. First, you just let the computer watch the empty scene for a few seconds. It learns what the background is supposed to look like, and it saves that as a reference. Then, for every new frame that comes in, it just subtracts the background from it, pixel by pixel. Anything that was the same just becomes black. The only things left are the things that were different.
And this shows it perfectly. You have the stable background. You have the current frame, which has a car driving through it. And when you subtract one from the other, poof, only the car remains. The road, the sky, the buildings, they all cancel each other out. This is a fundamental technique used in everything from home security cameras to highway traffic sensors.
So up to this point, we've only been changing a pixel's value, its brightness. But what happens if we stop changing what the pixel is and start changing where the pixel is? This is where things get really, really fun.
Think about it. Everything we've done, adjusting contrast, finding edges, subtracting backgrounds, was all about changing the numbers in the grid. A pixel that started at position 10, 20 stayed at position 10, 20. Now we're going to pick that pixel up and move it to a totally new spot.
This is called a geometric transformation. It's an algorithm that takes a pixel's original address, its XY coordinates, and calculates a new address for it to move to. Honestly, the best way to think about it is like a digital funhouse mirror. It can stretch and shrink and twist the image just by telling all the pixels where to go.
And you use these all the time without even thinking about it. When you resize a photo, that's scaling. When you straighten out a crooked horizon, that's rotation. But then you can get into the really wild stuff, like the non-linear warps that create those crazy swirl and ripple effects in photo apps. All of it is just algorithms moving pixels around.
So we went from this simple idea, an image is just a grid of numbers, all the way to enhancing it, finding objects in it, tracking motion, and even completely warping its reality. By breaking images down into simple data, we've given computers a really powerful way to interact with our world. And that leaves us with a pretty big question, right? Now that computers can see our world with this much detail, what are we going to ask them to look for next?